Hello, my name is Dylan Hedrick. I'm from Team 122. My teammates are Roger Liu and Jordan Zhang. Our project was to predict Canopy polarization reflectivity based on sky conditions. The purpose behind our project is just that when sky conditions and weather strongly affect the polarized reflectance measured by remote sensors, more specifically the degree of linear polarization measured from these sensors in cornfields, is much more homogeneous and similar and just noisy in general on cloudy days versus sunny days, which significantly impacts the correction techniques that are used when accounting for reflectance effects. To this end, we wanted to develop a model that predicts the polarized reflectance um, on these cornfields, given only the input of the sky conditions. Here is some examples of our data. We got images of the sky cam from a sky cam just throughout the day, whether cloudy or sunny that we used, and as well as panoramic images of the cornfields, which then were applied a filter based off the UV light levels detected from the sensors throughout the day. So our first model was trained only on these SkyCam images, and pretty much its purpose was to label these images either cloudy or sunny, based off the RGB channels in the image itself using a 2D CNN. And then the results of this model were fairly accurate and fairly high, or fairly good, at just predicting the sunny or cloudy images based off that and labeling them as such. And these labels are important for our second model, which takes these images as a basis point to verify the model's working. The way the second model works is that it takes the UV filtered images of the cornfield, which are split up into 2 or 3 images at least, and then we submit those images to the model, and the model compares the images, and if they are similar, that means that day, that time, it was a cloudy day, and then you check with the sky condition at that time and make sure that the model is correct. And then at the same point, if the two images are different, that means that it was sunny, and then you check with the sky condition if it's correct. This works because, as mentioned before, the measurements from the sensors are very homogeneous on cloudy days, meaning that the actual images that it would take, or the data it would take, is all very noisy and all very homogeneous with one another, meaning that whenever you apply these data to the images, as you see here on our results tab, the images look very similar. They're hard to distinguish anything out of them, and they all just look the same, which our model was able to correctly predict from these images that were inputted into it. So how it works is these images are paired together and then inputted into the model, and then it compares this image on the left with the image on the right. And if it sees that they are very similar, it says, oh, this is a cloudy image. And it checks with the label data from the first model and says, oh, yeah, it was cloudy, so I'm right. However, on the left side, you can see with the sunny days, you can make out the cornfield, parts of the cornfield just in the image, as well as just some of the background stuff, which makes the model say, oh, this is a sunny day, because I actually can tell the difference between these different images. And then it checks with the labeled data from the cornfield, or from the first model, and says, oh yeah, that's correct. Thank you for watching.